Swayam Prabha. Digital India. Educated India.
Welcome to this 8th lecture in the particle characterization course. In the last lecture, we started discussing some static methods for characterizing particle size. We initially discussed various microscopic techniques for doing size analysis, and later we started discussing methods based on light scattering. Initially, we discussed how light is attenuated during its passage through a suspension of particles, and how by looking at the extent of attenuation we can estimate both the concentration of particles in suspension as well as the surface area or the scattering area of particles that are in suspension, and from that estimate the size of particles that are suspended in the fluid. Then towards the end of the lecture, we started discussing scattering characteristics of single particles, particularly spherically shaped particles. And I mentioned that essentially the scattered light intensity from a particle is proportional to the incident light intensity, but scattering also depends on parameters such as the wavelength of the light, the refractive index of the medium that the particle is suspended in, the size of the particle, as well as the scattering angle. And we also discussed the fact that light, when the incident light is polarized, the scattered light also tends to carry forward the same polarization. So if light is polarized in two directions, one parallel to the scattering plane and one perpendicular to the scattering plane, then the scattered light will also be polarized in a similar fashion. So essentially the intensity of the scattered light is the algebraic sum of the intensities in a plane that is parallel to the scattering plane and in a plane that is perpendicular to the scattering plane. Now when we look at light scattering characteristics of a particle that is suspended in a medium, there are really two dimensionless parameters that are very crucial to consider. The first one is alpha, which is defined as pi times d over lambda, where d is the particle size in micrometers and lambda is the wavelength of incident light. Again, for visible light, the range of wavelength is roughly from 0.4 to 0.8 micrometers, and laser is somewhere in the middle of this wavelength range. So if you look at this ratio, why is it so critical? When this parameter alpha is much smaller than 1, this is called the Rayleigh scattering regime. When alpha is of the order of 1, this is called the Mie scattering regime. And it turns out that the laws that govern scattering of incident light vary greatly depending on whether you are in the Rayleigh regime of scattering or in the Mie scattering regime. Of course, when alpha is much greater than 1, you can essentially go back to microscopes, because now you are in a size range where the particles are actually visible to the naked eye, and certainly with microscopy of reasonable magnification you can study the size as well as shape characteristics of these particles very well. So, alpha much greater than 1 corresponds to the so called optical regime. So, in the remainder of this lecture we are going to focus more on the Rayleigh regime and the Mie scattering regime. The other dimensionless parameter that is important to consider is of course the refractive index. So, m, the refractive index, can be defined as c over Vp, where c is the velocity of light in vacuum and Vp is the velocity of light through the material of concern. So, if your particle is alumina, then the Vp value that we consider would be the velocity at which light is transmitted through alumina as a material. However, it is very rare that we consider particles that are suspended in vacuum. Most commonly the particles that we are looking at will be suspended in a fluid, whether it is air or water or some other gaseous or liquid material. It is most likely that there will be a medium in which the particle is suspended. In that case we talk about a relative refractive index MR, which can be defined as Vm over Vp, where Vm is the velocity of light transmission through the medium in which the particle is suspended, and Vp still remains the velocity of light transmission through the material that the particle is made of. Now, when you consider these two cases, when should you use this and when should you use that? Obviously, when you have particles that are suspended in vacuum, you can go back to your definition of the absolute refractive index. But even in cases of aerosols, that is where the particles are suspended in air, most of the time it is a reasonable assumption to say that Vm is approximately equal to c. So, in the case of airborne particles, you are most of the time okay using m as your refractive index. However, when you talk about particles that are suspended in liquids, there is a huge degradation in the velocity of light transmission through a liquid compared to through vacuum or through a gaseous medium. So, this definition is applicable predominantly for particles suspended in vacuum and air, whereas this definition is something you use for particles that are suspended in liquids. And when we discuss use of light scattering as a technique to measure particle size, and you look at practical applications in which this method is used, they are roughly equally divided into particulate suspensions in air and other gases and particulate suspensions in water and other liquids. So, both cases are equally important in terms of manufacturing industries and the prevalence of use of light scattering techniques for particle size characterization. So, it is important to keep in mind these two definitions. In the discussion that follows, just for simplicity's sake, we will use m as the refractive index, but keep in mind that when we talk about m, in the case of particles in liquids, what we are really talking about is the relative refractive index. Okay, so let us first talk about the alpha much less than 1 or the Rayleigh scattering regime. In this regime, obviously the particles are much smaller than the wavelength of the incident radiation, and the relationship between particle size and the various other parameters to the scattering characteristics of the particle can be established fairly conclusively. As we will see later on, the Mie scattering regime is actually much harder to deal with. There is a lot of variability in the scattering signal, and prediction of scattering intensity as a function of theta becomes very complex. But in the Rayleigh scattering regime, there are well established formulae for calculating scattered light intensity as a function of the various parameters that are involved. And again, we have to split the contribution into I1 and I2. I1 is equal to I0 times pi to the power 4 d to the power 6 over 8 r squared lambda to the power 4 times m squared minus 1 over m squared plus 2 the whole squared. I do not expect you to remember the formula, but make sure you understand the functional dependencies that you see here. The first thing is I1, which is scattering in a perpendicular plane to the scattering plane, is not theta dependent. It is a constant value for all theta. So, the scattering angle does not enter as a parameter. The second thing is you see the d to the power 6 dependence. As I mentioned in the last lecture, scattering intensity goes as dp to the power 6. So, there is a very steep drop in scattered light intensity as the particle size decreases. R, by the way, is the distance of separation between the observer and the object. And like most forces that are distance dependent, there is an inverse relationship between distance and the force, just like magnetic force or electrical force. There is always a sensitive dependence on the distance of separation from the field and where the measurements are taken. And finally, lambda in this case also appears in the denominator, and the dependence on m is given there. Now, I2 is simply the same multiplied by a cos squared theta parameter. So, the theta dependence really comes in I2, and the total scattering intensity I, which is equal to I1 plus I2, is then given by I0 times these two terms times 1 plus cos squared theta. So, this is the overall expression for scattered light intensity from a spherical particle. Now, if you plot this as a function of theta, so theta goes from 0 to 180, and let us say that you are plotting a relative intensity here. I1 will essentially have a constant profile with respect to theta. Let us say that this is 1. I2 has a theta dependence, and so it will actually have a minimum at a theta of 90 and have a characteristic shape that looks like this. So, the total intensity I will then have a shape that looks like this. So, this is I equals I1 plus I2. Of course, this will be in relative terms it will be 2. So, if you are trying to measure scattered light intensity from a spherical particle that is in the Rayleigh scattering regime, you can see that the dependencies are very well established. The expected relationship between scattering angle theta and the scattering intensity is also well established, predicted, and it can be measured and validated as well. So, particle size measurement in the Rayleigh regime is actually the easiest to accomplish. Now, what do we, when we say alpha much less than 1, what are the actual sizes we are talking about? It has to be roughly in the 1 micron size range. Now, when d is equal to 1 micron, then this is let us say 3.14. So, this works out to about 3.14 times 1 divided by, let us say, 0.6, it works out to roughly 5, which is clearly not much less than 1. So, when we talk about alpha values being much smaller than 1, we are talking about submicron particles. A 0.1 micron size particle will then correspond to an alpha value of roughly 0.5, right. A 0.01 micron sized particle will correspond to 0.05 here, which is much smaller than 1. So, now what is this correspond to? 100 nanometers. So, the Rayleigh scattering regime in terms of actual numbers essentially starts where nano ends. I mentioned earlier that nano is a size range that is conventionally defined as 1 to 100 nanometers. 100 nanometers to roughly 500 nanometers or so is what we call the submicron regime, and that is where the Rayleigh scattering effectively happens. So, when you use particle counters that are using light scattering as the basic principle, they are most accurate in the size range of roughly less than a micron to more than 100 nanometers. Let us consider the Mie scattering regime next. So, when alpha is roughly equal to 1, we call this the Mie scattering regime. In this size range, again there is a linear relationship between I1, I2 and I0, but then you introduce something called a lowercase I1, which is called the Mie scattering parameter. And the actual expression then becomes I0 times I1 divided by lambda squared over 8 pi squared r squared, and similarly I2 equals I0 times I2 times lambda squared over 8 pi squared r squared, and so I equals I0 times I1 plus I2 times lambda squared by 8 pi squared r squared. The complexity is actually in this I parameter. I1 and I2 have very complex dependencies on theta and the refractive index parameter m, and unlike the Rayleigh scattering regime where these predictions are valid irrespective of the medium and the particle, the materials that they are made of, as well as the scattering angle ranging from 0 to 180. In the Mie scattering regime, each of these becomes also system dependent. So, they become more what we call constitutive laws. They are not universally applicable to all fluids and all particles, but must be essentially recalibrated for every combination of fluid and particle. And so, if you look at, if you try to plot, for example, theta versus I in the Mie scattering regime, the relationship that you see will not be as clear cut as what we saw in the Rayleigh scattering regime, but it will actually show a lot of scatter and also non-monotonic behavior, which is roughly cyclical in character when you go from 0 to 180, and it will have a significant dependence, as I said, on the actual materials that are under consideration. So, when you think about it, then how do you even use this signal to predict size? Because what this would tell me is for the same particle size you can have multiple intensity values, and for the same intensity value there could be multiple particle sizes that contribute to that intensity value. So, the interpretation of the scattering spectrum in the Mie regime to calculate particle size becomes somewhat questionable. So, for particles that are roughly in the 1 to half a micron range, the uncertainty in the measurement is very high. For particles that are larger, again you can go back to optical methods of analysis. For particles that are smaller, you can use a Rayleigh scattering calculations. It's the particles that are in the range where they are too fine to be characterized using conventional optics, they are too coarse to fit into the Rayleigh regime, that the error in the measurement or the uncertainty in the measurement is highest. So when we look at particle counters in general and particle size analyzers, most of them tend to say that in situ calibration is necessary. In other words, you cannot rely upon a calibration that's done in a standards lab, for example, and use that to evaluate your particular samples. You have to do the calibration in your lab using materials that are very similar to your system that's under consideration, and you have to fix all the geometrical factors in your system, as well as the wavelength of radiation, and essentially you have to recalibrate every time any of these parameters changes. And so that is one of the difficulties in using this technique to handle particles in that size range. So in the next lecture we'll talk about some alternative methods of measuring particles that are in that intermediate size range that's very difficult to measure. But as you will realize, the size range that is smaller than 100 nanometers obviously is also difficult to measure because of that other effect that we talked about, that as particle size decreases, there is a very, very steep drop off in the intensity of the scattered light. So up to, let's say, 100 nanometers, you are in the Rayleigh scattering regime, and it's possible to measure particle size fairly well. But what do you do when size drops below that value? Let's say that you still want to use light scattering as your technique. One reason is in this size range, in the 100 nanometers and less size range, there are very, very few techniques that are any better than light scattering, even with the limitations that it has. And so you want to try and make light scattering work even for particles that are smaller. But how do you do it? Same question I think I posed in the last lecture. When you think about it, the only way you can do it is essentially by taking particles that are in this size range and making them grow larger so that the size increases in a controlled manner to a size where you can use Rayleigh scattering technique to detect the size. So how do you do that? How do you grow the size of a particle? By making something condense on it, right? So there are these particle sizing instruments which are known as condensation nuclei counters or condensation particle counters, which essentially do exactly this. So we'll talk about those in some detail now. So particles in the 1 to 100 nanometer size range, they are called nanoparticles. Before nano became a catchphrase, they used to be known as ultrafine particles. Again, the challenge with these particles is the fact that the scattered light intensity drops off very rapidly, so you don't get a strong enough signal, and the noise in the measurement sometimes dominates over the signal, right? So how do we deal with these particles? Well, the first thing to think about is, how do these particles happen? What causes the generation of particles in this very, very fine size range? If you look at particle size distribution in nature, suppose you go outside and take a sampling of the air and look at particle counts as a function of particle size. It's very interesting that no matter what region of the world you are in or what the topography of the land is, you get essentially the same signal or characteristic shape of this curve. So if you plot size on this axis versus, let's say, count on the vertical axis, and you plot this all the way from 1 nanometer, let us say, to 10, 100, 1 micrometer, 10 micrometers, 100 micrometers, and so on. What type of shape do you expect? Do you have any idea? Will it look like this, or like this, like this? Yeah, actually the prevailing shape is trimodal. It will have 3 distinct peaks. Now the heights of these peaks may be different depending on where you do the sampling. I mean, if you are in a highly polluted city, all these peaks may be very high, whereas if you are in a clean area, all these peaks may be very low, but they all retain this trimodal characteristic. And what is the reason for that? The very fine particles in this distribution are essentially caused by condensation of vapors. So for example, in the atmosphere you have all these chemical vapors that are being emitted into the environment, which will condense, and when they condense they will form what are known as nuclei or nucleates, right. So that is basically what this peak represents. It is the first condensed phase nuclei that are formed when a phase change occurs from vapor phase to either solid or liquid phase. So these nuclei that form could be in solid form or it could be in liquid form. In class, the simplest example of this is of course formation of the initial nuclei of rain. Rain happens because water vapor condenses to form these very fine nuclei. So how does this happen? What is the next stage in the formation of a raindrop? Agglomeration. So this is the what is known as a growth phase. These nuclei find each other and start agglomerating, and eventually they reach a size that brings them from here to here. So this is region 1, this is region 2. So a particle, for example a water droplet that was nucleated here eventually becomes a large enough raindrop here, and then it starts to rain. So it is actually an interesting fact that you would think that in areas where the temperature is suddenly lowered, there is a tendency for rain to happen, but actually it turns out that is not enough. The reason, for example, that cities like Chennai have very low rainfall is because we have a kind of a worst case scenario. We have high emissions from, for example, traffic on the roads and other reasons, but at the same time Chennai is not a highly industrialized city. Now why does industry help? Usually you think of industries also as polluting, right, but from the viewpoint of rain you actually require industries because they emit particles, very fine particles into the atmosphere, and it is these particles that actually serve as the initial sites where these nuclei can form, because now you are introducing a heterogeneous feature. Homogeneous nucleation is very difficult in terms of overcoming the energy barriers associated with it. Heterogeneous nucleation can happen like that. So in other words, even if conditions are very conducive to the formation of rain droplets, if you do not have a sufficient amount of suspended particulates in the environment, rain will not happen. So you actually need a certain amount of pollution in the atmosphere for rain to begin happening. And so the nuclei that we are talking about here can either form in a homogeneous mode or in a heterogeneous mode, and heterogeneous mode always has a lower energy barrier, and so it is much more feasible compared to homogeneous nucleation. The growth phase is essentially the phase where the initially formed nuclei find their nearest neighbor and start agglomerating. The third phase now is distinctly different from these two, and it's actually most of the time not related to these two. It comes from an independent source. For example, this could be just your dust particles, or again it could be industry emissions that are in a larger size range compared to the types of emissions that are participating here. Or this could also be due to spewing aerosols that are getting into the environment. So the source here is distinctly different from the source of particles in these two cases. So as I mentioned, this is for the outdoor environment. Now how about indoor? What kind of distribution would we expect to see? Suppose you take the sample here in this room. What would be the size distribution you would expect? Again, we go from 1 nanometer to 10 to 100 to 1 micrometer to 10 to 100, and you're looking at the counts. Do you think the same trimodal distribution will prevail in the case of the indoor environment also? Actually, again the qualitative nature of the size distribution remains the same. You still see a trimodal size distribution even in indoor environments. Again, the actual magnitude of the peaks, the scale itself can change significantly. For example, if this is a clean room, a clean room is a facility that is designed to operate with a very fixed level of contaminants in air, including particles. So for example, and we will discuss this in more detail in future lectures, when you talk about a class 100 clean room, what it means is that per cubic foot of the air that's inside the room, you can have no more than 100 particles that are 0.5 microns and larger per cubic foot of the air. So under those conditions, obviously these peaks are going to be very small because it's a well controlled and cleaned environment. However, it's very interesting and intriguing that in terms of the qualitative nature of the particle size distribution, it retains this trimodal characteristic. And the reason for that is that the first phenomenon of condensation and nucleation also happens inside even a room like this. Now why is that? Well, there's a couple of reasons. One is that all materials outgas. Outgassing is a phenomenon that is obviously not visible to you, but any material that's sitting here is constantly emitting molecules into the environment. Every material, including humans, is a constant source of emissions in the vapor phase. So we are constantly adding vapor phase constituents to this room. So as that happens, and again as they find some heterogeneous sites to promote that nucleation, they will start nucleating very fine droplets. Again, you cannot see it, but actually if I were to, let's say, darken this room and illuminate it with a fiber light, you can actually start seeing these very fine particles and droplets in the air, right? And of course, as long as condensation and nucleation are going on, agglomeration and growth are associated mechanisms. Although the extent to which this happens again depends on how clean the room is. For example, in a well designed clean room, particles are present in a very dilute form. The number of particles per unit volume is very low. So the probability of one nucleated droplet finding another one is also very low. So agglomeration kinetics are going to be highly slowed down in a clean room type of environment versus an uncontrolled environment. Also, in a clean room environment which has very directed airflow, these fine droplets that are being produced will be quickly directed to go in a certain way and removed from the room. So they will never have an opportunity to find each other and start growing. So in a controlled environment, the phase of going from here to here may only happen to a very limited extent. So in a highly clean environment, you may get a peak like this, which is very low, compared to a room like this where this peak may be quite high. This room, for example, just in terms of clean room classes, it's probably about 1 million. And just to give you a perspective, right? If you actually took a particle counter and measured particles in this room, you will find there is at least 1 million particles per cubic foot that is half a micron and larger. Even though none of them is visible, you would think that this is a clean room, but it's really not. It's a clean room, but that's different from a clean room. It depends on whether you write it as one word or two words. Okay, clean room is something that is a very special thing. So where is this source? Actually, the most common source for particles in this region in an indoor environment is humans. Because again, we may not realize it, but we are constantly shedding. We are shedding skin flakes, we are shedding fibers from our clothing. As we speak, we are shedding saliva droplets, hair is falling out. All these are contributing to large particles that are present even in a semi-clean environment. Also, if inside that indoor facility you have tools that are operating or equipment that are in motion, or you have processes that are taking place, each of these is a source of particles in this size range. And just as an example, if you take two metal surfaces and rub them against each other, you will generate a shower of particles that are all in this size range of 10 to 100 microns. Again, it may not be visible to you, but you take a particle counter and you measure it, you just get this huge burst of particles. So any sliding motion, any abrasive motion generates a huge number of particles in this third peak. Same thing with the spewing out of aerosols. If you are using equipment that's using an oil or a grease or a lubricant, these lubricants are constantly being spewed into the air as the process takes place, as the equipment operates. Again, even though these may not be visible to you, you can detect them using a particle counter. So clearly, particles that are present either in an outdoor environment or in an indoor environment, either in a controlled environment or in an uncontrolled environment, all have distinct sources of particles that are spread across this entire size spectrum. And that is why it is important to measure particles that are below 100 nanometers, because otherwise you are going to miss these very, very fine droplets and particles that are present. Now, why is it important? Well, in a way, they are the precursors to everything that happens afterwards, right? If you are trying to minimize the number of particles in an atmosphere, what you should do is eliminate this process. If you can eliminate the condensation and nucleation process, then this process won't even get started. And usually the larger particle range is much easier to handle. There are very, very well identified and fixed sources for such particles, and I wouldn't say it's trivial, but it's a relatively easy exercise to get rid of particles in this size range. But in this size range, again, there's a saying that if you cannot measure something, you cannot control it. You have to be able to measure quantitatively in order to be able to control. So that is why the measurement ability in the sub 100 nanometer size range is very, very important in many, particularly precision manufacturing industries such as semiconductors and so on. So how do you do it? Again, it goes back to the problem that we started talking about earlier. Given that there is this steep fall in scattering intensity as the size drops below 100 nanometers, how do you measure it? Well, going back to these curves, essentially what we try to do is, if you are trying to measure the size of a particle in this size range, you introduce a vapor which condenses on top of this particle and grows a sufficiently thick layer so that this particle size is migrated from this range to a more measurable range. So if you have a collection of particles in this size range and you do this condensation process on top of all these particles, they are all going to grow to a size where now they are detectable, right? And so that's how basically these condensation nuclei counters or condensation particle counters work. So condensation particle counter is very, very similar to the laser particle counters that we have been discussing so far. it includes that as one of the stages in the process, but it adds a couple of stages to it. So what you do is you take this ultrafine particle population which is suspended in some fluid, whether it's gaseous or liquid, and you take it through a stage that is called a saturator and another stage that is called a condenser, and then this stream is input into the particle counter, and the rest of it essentially follows the same light scattering principles that we have outlined earlier. So in a condensation nuclei counter or CNC, the part that we have added is really this upstream part. So what exactly are we doing here? We are taking the ultrafine particles that are, for example, in air. You are introducing here a condensable vapor, but you keep the temperature slightly high. So this temperature here may be slightly greater than room temperature. At the next stage, you just slightly lower the temperature, which is sufficient to relieve the saturation that is present and cause condensation to happen. So condensation will then happen on all these ultrafine particles and they will be introduced into the particle counter as enlarged particles because of the condensation that has taken place. So it's fairly simple, right, in principle. What is the problem with this methodology, or what are some of the drawbacks? One of the difficulties is you can measure the size distribution of the grown particles, but from that can you actually extract the size distribution of the original particles? Well, you could, but it will take a lot of work. Essentially you have to do a calibration. You have to do this process and possibly use an independent measurement technique to look at the kinetics of how the vapor that you are introducing condenses on particles of various sizes. So if you were to do that exercise, then you could essentially take the data you get from here and extract the original size distribution that was present. But there is actually a cleaner or smarter way to do it, which we will discuss very soon. Before that, should talk about how do you do the saturation? What are some of the vapors that are commonly used to make these to grow these ultrafine particles to a fine particle size range? You typically do that using organic solvents such as butanol, isopropanol, ethanol. The problem with butanol and isopropanol is they are toxic and they also have a kind of a bad smell, but they are very, very good. Now what are the features you look for in this type of a vapor? It should be easily condensable, and it should be able to condense both on hydrophobic as well as hydrophilic surfaces, because the particles that you have suspended may or may not be hydrophobic. So water may not always work as the medium to condense on the particles, whereas many of these alcohols have a hydrophobic part and a hydrophilic part. So they are able to condense on either hydrophobic or hydrophilic particles. In the case of the hydrophobic particle, the hydrophobic portion of this molecule will attach itself to the particle, whereas in the case of a hydrophilic particle, the hydrophilic portion of this molecule will attach itself to the particle. So they can condense on both types of materials. Other commonly used solvents are diethylene glycol, dibutyl phthalate, hexanol, and so on. So these are all organic solvents that have high vapor pressure. See, the other requirement for these materials is once they have condensed and you have done the particle size analysis, you want to be able to rinse these off also, right? You don't want them to permanently stay attached to the particle, because then they become a contaminant in the process. So these are materials that can be easily re-evaporated. You can simply take the temperature high and you can essentially recover the virgin particles, or worst case you can use another solvent to essentially remove these condensed layers on the particle. So that is one of the requirements. Now, so these are the organic solvents that are typically used in a condensation nuclei counter or condensation particle counter, but there are alternative fluids you can use also. Water certainly is very attractive because, I mean, if you talk about liquid solvents in general, water is the most convenient medium to use. The problem is water cannot be used for hydrophobic surfaces. So the use of water is normally limited to surfaces that are known to be hydrophilic, easily wetted surfaces. However, more recent work has led to the development of surfactants which can be used that promotes the wetting even of hydrophobic surfaces using water. So water plus trace amounts of surfactant are now being used to condense on particles that are even hydrophobic. Other materials that are used in this application are inert materials, for example perfluorocarbons, even noble gases like argon, helium and so on. Nitrogen can be used, even O2 and H2 have been used. But if you look at usage of solvents in condensation particle counters in general, the most popular ones are water, either with or without surfactant, and ethanol. The only problem with ethanol is it has beautiful properties. It has very high condensation potential and high evaporation potential. There are no toxic effects. The only difficulty with ethanol is sometimes procurement. Methanol is much easier to obtain compared to ethanol, so prices are higher, availability is lower, but you only require really small quantities to do this test. So it's not such a big issue as far as doing this testing is concerned. Now this method that we have been discussing so far, the condensation nuclei counter method, really works for fine droplets or ultrafine materials in air and other gases. How about if they are in a liquid? Can you still use this technique? It's actually not possible to use a condensation nuclei counting technique for particles that are suspended in liquids. So the alternative is essentially to measure the fine particle level using quantitative methods, typically gravimetric methods, that estimate total non-volatile residue in the liquid. In other words, just boil off the liquid and look at what is left. Look at the non-volatiles that are present in the liquid. A substantial fraction of those non-volatiles will be particles that are in the ultrafine size range. It's not a perfect method, but the ability to count and size ultrafine particles in liquids is not nearly as well developed as the ability to characterize them in gases. How about surfaces? If you are trying to characterize presence of ultrafine particles on a surface like this, again the same difficulties exist. Light scattering, now you have actually a double jeopardy. Light scattering intensity from the particles is very low, but at the same time the noise, which is the scattering from the surface itself, is very high. So use of light scattering techniques to detect ultrafine particles on surfaces is even harder than detecting them in gases or liquids. But lately a variant of this technique has emerged where you do what's known as surface condensation, again of condensable vapors. And the principle is the same. You take these ultrafine particles and by condensing vapors on them, you grow them to a size where they now become large enough that the signal, the scattering signal you get from them is comparable to or larger than the noise that you get from the surface itself. So the use of condensable vapors to grow particles ultrafine particles on surfaces to a larger size range in order to do scattering technique based measurements is gaining in popularity. But we still come back to the fundamental question of how do you translate the sizes that you measure with a condensation nuclei counter to the sizes of the ultrafine particles that were present to begin with. So just think about that. In the next lecture we will start out by describing a method that enables us to do that. Any questions? Okay, see you in the next lecture then.